So what is positioning? Simply said, positioning is knowing where on Earth you are. Okay, that's as simple as that. In the earlier days, people used to do the positioning of themselves by the stars and the moons and the suns. Later in the 20th century, we came up with something called LORAN. It's a long range navigation system. It's a radio transmitter, high frequency radio transmitter that are set in the coastal region, and they can transmit a long distance radio waves, and the vessels or the ships can receive those long range radio signals, and they can navigate as per those signals. They can find the distance from those radio stations and they can triangulate their position. And then came World War. Yes, war is a terrible thing for humanity, but war is also good for the technology, and it gave rise to many different technologies that we use today. So one of those technologies were the GPS. In the 1960s, the US Department of Defense or the Ministry of Defense, they decided that they need to pinpoint bombing, especially Russia. They need to bomb Russia very accurately, and for that purpose, they sent some 30 satellites into the orbit. And those satellites, they are placed at a 55-degree angle, 55-degree inclination with each other in 6 different orbits. There are 4 different satellites in each and every orbit, and there are 6 different orbits, so there are at a time 24 working satellites. At any given time, anywhere on Earth, you are always going to get 4 satellites, and that's what is required to find your position very accurately. So as the time progressed, the Russian caught up. They sent their own satellites into the space, and they got their 24 satellites for themselves. And then the Chinese and the European Union caught up, and they also sent satellites in the space for their own purpose. And the American group of satellites are called Napster Constellation. This is American, and then the Russian group of satellites are called GLONASS, and the Chinese satellites are called Beidou, and the European satellites are called Galileo. So earlier we had GPS, that's with the Napster Constellation, that is the global positioning system. Now with all these satellites, they all are global positioning system. They are moving around the Earth. Anybody with a suitable device can receive all of them, and together they are called as a GNSS or Global Navigation Satellite System, and they contains all of them. Now there are some regional satellites like Japan. They have a QZSS, quasi-zenith satellite system, and they move in almost like a figure of 8 over the Japan Peninsula and Japan area of the Japan. And India also have their own satellite system, which are called IRNSS. Okay, that's a regional satellite system, a regional navigational satellite system. Now to find any position on the surface of the Earth with the help of a satellite, we need minimum of 4 satellites. So how does that work? If I am standing on the surface of the Earth and the satellites are in the orbit, so I need minimum of 4 satellites in the orbit. Okay, they are about 20,200 kilometers above that GPS satellites are 20,200 kilometers above the surface of the Earth. And the satellites, they send out a signal in a typical frequency. They are called L1 and L2. Primarily, these 2 frequencies are received by the receiver. But as a civilian, we can use L1 frequency only in our mobile phone, in our GPS receiver. And this L1 has just a frequency, but a code which is called CA, or the course acquisition code, that runs on top of this frequency. Okay, so we are using L1CA code. Now in earlier times, the L1CA code had an accuracy of itself about 80 to 90 meter, and that was not good. as soon as the selective availability was gone, our GPS position was as accurate within 5 to 7 meter or about 10 meter in the worst case scenario. So we need 4 satellites to find our position. I told you before that there are 6 orbits and there are 4 satellites in each orbit. So no matter where you are on Earth, you will always receive at least 4 satellites. Now let me talk to you a little bit about the frequency and the code that the satellites are transmitting. Now every satellite is transmitting a signal towards the Earth. It's a radio frequency. Let's take L1 frequency. Okay. So L1 frequency is transmitted towards the Earth. So what does the L1 frequency contains? There are many different messages are there in the L1 frequency that is riding on top of the frequency, and we call them PRC or Pseudo Random Code. This contains primarily the time of signal generation, what time the signal has left the satellite, and the timing for each and every packet of PRC of L1 frequency CA code is 1 millisecond. So every 1 millisecond, one packet of CA code or the PRC is riding on this frequency. It gets some navigational message also. It contains some navigational message also. It also have ephemeris, that is the satellite data, the health of the satellite or where the satellite is on the orbit and where it is going to be in the orbit. There are many more data that are transmitted. So we mostly need this time data. What time the frequency has left the satellite, and then in our receiver we also generate a similar code, and then we try to match this pseudo random code. So pseudo random means it looks random, but it is not random. It is almost like this. So this kind of a message is coming from the satellite, and the receiver is also generating exactly similar kind of a signal, and the receiver then tries to match the signal with each other, and they try to find what is the time gap between them, like this portion and this portion matching, and what is the time difference between the signals. So it's the job of the receiver to find how much time for the signal to travel from the satellite to the receiver. It can calculate the distance. So every receiver calculates the distance to the satellite by its pseudo-random code. Now this pseudo-random code, the CA code, will differ from satellite to satellite. So it's the job of the receiver to quickly generate those signals, same signals, and match the timing to find the distance to the satellite. And with 4 distances, the receiver itself very accurately can pinpoint where on Earth we are. And in our surveying, we call that a trilateration. And the exact same thing that happens not only with GPS, this happens with GLONASS, Galileo, Beidou, IRNSS or QZSS, no matter what kind of satellite is there. But the problem remains that the signals, they are traveling from the outer space to the receiver through a dense and thick ionosphere and atmosphere. There may be a rain cloud, so it has to pass through the heavy clouds. So it gets delayed, and we call this an ionospheric error. Let's now look at what are the errors a GPS can contribute into our positioning system. So the first and foremost is satellite clock error, which can contribute to plus minus 1 meter. And then atmospheric error or the ionospheric error. It can contribute to anywhere between 1 meter to 20 meter. So ionospheric error or the atmospheric error is the biggest contributor to the GPS error that we are receiving in our receiver. Third is orbital error, and this can contribute to plus minus 2 meter. You see, the satellites are in orbit. Though they are 20,000 kilometers from the Earth, there may not be any atmosphere putting a drag on the satellites, but there are solar flares, right? There is a solar wind, and they create a drag on the satellites. So over time, the satellites will slow down and their orbit will degrade. So orbital error. Then we got multipath error, which can contribute to plus minus 1 meter. Multipath error means your GPS signal is bouncing off from hard deck of the vessel, or from the water surface, or from a building, a facade, a glass wall, and that takes the signal a little bit more time to reach your receiver, and that causes an error into the receiver. Okay, and the last but not the least is your receiver noise, and that can contribute to plus minus 1 meter. Receiver noise means that you got a receiver, you got a cable connection from the receiver to the antenna. So there is a two different connectors. One is connecting to the receiver and another one is connecting to the antenna. And if your connectors are not good, if it has a salt ingression, or maybe it's a little bit rusty, or the cable is frail, then it can contribute a receiver noise. Then you have a power cable. There may be power fluctuation, 24 volt or 12 volt DC that you are using in your receiver. It can have a power fluctuation. And then you also have a data cable that is coming out from the GPS receiver into your computer system. And that can also contribute into the receiver noise. So they all contribute. And together, if we look at it, they all are additive. They're not individual. So with an additive, the GPS can have anywhere between half a meter to 25 meters of error in its position. So we can divide our GPS or GNSS system in mainly three different segments. The first and foremost is your space segment, where the satellites are. And then all the data is monitored and controlled at the control segment. The head office is in Colorado Springs, but there are a lot of monitoring stations in and around the equatorial region, Diego Garcia, Hawaii, Kwazulu Island, and some I can't remember exactly. I'll put it into the screen here for you. So they are being monitored constantly, and whatever update is required, whatever the orbital correction or the ephemeris correction is required, they are being uploaded back into the satellite again. If some orbit degrades, they can boost the satellite orbit to the right orbit. So all this is done from the control station, and you don't even realize that there are thousands of people working day and night to make sure that you get your position as accurate as possible. And then there is a user segment where we are the user. We are using the positioning device. Now you may ask, what is the contribution of a GPS? What it does, positioning, if I am not going for surveying, what positioning has to do? Just remember, you use your Google map to navigate from one place to another place, and that is one of the smallest use that we do with the GPS. The biggest user of the GPS are the banks, the railways, the aircraft, and big institutions where time is of most importance. So how is it possible that GPS gives you very accurate time? It's because GPS has something called an atomic clock. Millions of dollars of worth. No, it's not an atom bomb. It's an atomic clock. That's a cesium-132 atom. It's kept in a vacuum under magnetic influence, and it vibrates over 9 billion times every second. And that's how we are able to keep the timing very accurately. But what about my mobile phone or your normal GPS receiver in your watch? How costly are they? Believe me or not, they are less than 30 rupees or about 3 cents. Yes, but how come then this mobile phone that I am using can give me very accurate time? It's just because as soon as you are latching onto a satellite and you are getting a position, your clock on your mobile device, on your watch, on your GPS receiver gets updated every second. Okay? So we have discussed about the GPS errors. But how do we know what is the quality of the data that I am getting? What is the quality of my position data? And that is possible by knowing what is going to be my DOP. That is dilution of precision. And it depends on the satellite geometry. It means the satellite positions over my receiver position in the sky. If my receiver is here, if all the satellites are clumped together at one place, and that's a very bad geometry. We do not want all the satellites clumped together. So what happens? The range angle of cut are very acute. So the position cannot be properly defined. It can be within plus minus 50 meter, 100 meter, 1 kilometer or more. So then the DOP will increase. What DOP? That will be the PDOP, or the position dilution of precision. And we want the position dilution of precision to be anywhere from 1.8 or below. It is okay if the dilution of precision goes to up to 2.1, we can still use that data. But if it goes beyond 2.5, 3, 4, then the position data is very bad. You should not attempt to use that data. But how do you know when I am going to get a certain number of satellites in a good position? So, and what is a good position? So if your position is here, if the satellites are spread around the sky, and they will create a very good angle of cut. And that's a good position. And we have a website where you can go and you can plan. You can put your own position and date of observation, and you can see the availability of the satellite and the DOP value that you are going to get at that time with that number of satellites. I'll have that link in here and also put it into the description below. Please check it out. You must plan before you proceed for any kind of observation. Alternately, you can watch this video that I made a couple of months back. That gives you a lot of information about GPS or GNSS planning. Now this is about the position. Suppose you don't need a position. Sometimes surveyor has to go and use the vertical component of the GPS. And that is very important when you are going to establish a benchmark. If you are going to establish a new benchmark and you need to transfer it from an existing benchmark very far away, and you need a very good VDOP, that is the vertical dilution of precision. Okay, you need to see your VDOP is 1.8 or below. And then you can do the observation, and this information also you are going to get it in this GNSSplanning.com. So with all the GPS data that we are getting, or even with the GNSS data that we are getting, there is still some error that is coming into your receiver, and that can be as big as 5 to 7 meters. And that's not good when you are doing a precise survey. You need the most precise position as possible. So what do? There are mainly two different ways to get the position accurate, and we call that a differential. In the differential, there are two different types of system that we use. For first, we need a base station whose position is already fixed and we already know. We put a GPS antenna on top of that position, and then we observe the GPS position at that location, and that will give me certain amount of data which can be somewhere into this error ellipse between 5 to 7 meters. Okay, now this data is then being analyzed for the correction because of the satellite's range, for which we are getting this erroneous data, and that information is then transmitted back into the air, and you got a boat using the same GPS antenna, using the same kind of a GPS satellite that this base station is using, and they are getting an erroneous data in there. And when they use this differential data in their GPS data, they are applying it in here, and then they will get a very, very accurate data. So how accurate we are talking about? We are talking about somewhere between decimeter level, half a meter to 0.2 meter decimeter level, and that's quite good for general navigation or general bathymetry survey. But then we need more precise data. There is one more way to make your positioning data precise, as good as 3 to 5 centimeter, and that is called orbital and clock correction. Now this orbit and clock correction is similar to the differential system, the range correction that we have already seen, but here the range differences are being transmitted to the control segment, the control tower and the monitoring segment, and they then receive it, and they then analyze the clock error and the orbital error, and they transmit it back. They are transmitting it back, and then the vessel, they are receiving it, and they are applying that clock correction and the orbital correction, and that's very accurate within 3 to 5 centimeters. Now for the range correction, the closer you are to the base station or to the reference station, the more accurate your data will be. The further you go away from your base station, your data quality degrades. But that's not the case for orbit and clock correction. So a newer generation, upper version of a GPS receiver, of course it's a costlier one, they can receive the orbit and clock correction, and no matter where they are, how far away from the base station, they will always receive the orbit and clock correction, and their positioning system will be accurate within 3 to 5 centimeters. Now one question remains. You may be asking that how do I transmit the orbit and clock correction or the differential range correction to my vessel in the middle of the ocean, say 200 kilometers from the base station? How do I do it? So all these corrections are uploaded into a geostationary satellite. They're uploaded actually to all the geostationary satellites. And then the geostationary satellites are beaming back this data back to the user. So you are getting orbit and clock correction and the range correction from the geostationary satellite. So I hope you learned something new today. If you like this video, then I am sure that you want to watch out these 2 videos next. If you want to know more about the GPS and the DGPS system. So be good and always be curious. I'll see you soon.